Okay. Dylan, what are you doing? Okay. Oh, today, right, Dylan? Right, you tested it? Today? That's it. Come on there. Yeah. And there's a couple others.
Apologies. I'll have more demos next day. Entirely my fault. I put in the request for demos at like 10 p.m. last night, so of course they're not done yet, but I have a couple. Okay. We already did that. No, we already did that. Now, there are a variety of demos that we will be doing. This is eBlock, quick attendance, NA, Andrew, Daniel, no, Dylan, Eshwan, Jillian, Chloe, Co, Logan, Luca, no Luca, Luce, Luke, Milan, Nick, other Nick. Did you say Nick not here? Stop that. Ryan. Ryan? Nick Meyer, M before L. Tatum. Taylor. Thank you. Okay, this is a bit of review from last year. So I'm going to ask you to tell me what these are. Milan, what kind of change do you have where you get a new substance created? Yeah. So we are starting reactions as our new section. We're going to be balancing in here. We've already done nomenclature, so you'll be translating names into formula and then balancing equations, that sort of thing as well as a lot of practice of balancing. The next section after this, we're going to do the balancing, but with numbers. So you can predict the number of moles and the number of grams that are produced by the reaction. Oh, yeah, grab one. I gave your table, I thought. Oh, did you come in late? Lies. Lies. A new substance is created with new properties. With a chemical change, what's broken and reformed? Bonds. 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 James Bonds. So, as I said, I put in my list of, I have a number of demos I want to show for this. However, I put the list in at 10 o'clock last night, which is way too quick. Once I get you working on maybe some head demos, go see if I can just grab them, but that was way too quick to allowed to get that. But it doesn't take much of a demo to show the difference between a chemical and a physical change. Okay, so I have a table. Dylan? Eshwan? Chemical and physical change. But I'm actually breaking something. Why is it just a physical change?
Because they're not actually breaking the bonds.
Does anybody know what holds paper together? The fibers wound around. It's the type of bonding we'll talk about later. It's not a full chemical bond. They're attracted in the same, not in the same way, but you can think of it like magnets are attracted. It's much more like static electricity. Just molecules that have a positive and negative being attracted. That's what holds paper together, which is why if you put it in water and it gets wet, the fibers move apart. So there's no chemical bonding between the fibers. And so this is just a physical change. The paper is still the paper. If, however, you were to eat it, right now, is it undergoing a chemical or physical change? Really? Can enzymes break down paper in humans?
No. No, because they go into your stomach with the hydrochloric acid.
Yeah, it'll go in my stomach with some hydrochloric acid, but it'll still be paper fiber. Wood's pretty robust. I'm just getting my daily fiber. So the parts of your meal that are indigestible, we used to think was useless. And then one of the areas of research is discovered that no, fiber is really, really important, other than just our daily observation that your bowels require it. For the space program, they had to come up with a nutritional meal that was very low on weight. And so they took out all the fiber. They essentially made a meat jello. So it had all the nutrients, and they were like dense cubes, no fiber whatsoever, just dense cubes of nutrients. And they're like, astronauts, you eat this. And then it turns out you digest it, but your bowels don't get any kind of a workout. And that was really bad for the astronauts. They would have excessive farting and diarrhea. And it turns out that if you're in the middle of a spacecraft covered in an astronaut suit, diarrhea may not be the best thing that you want to be doing at that moment. And so they learned about the importance of fiber. So actually, now if I was, say, a fungus or a cow that could digest cellulose, I might actually get some nutrients in it. But this is still all just physical change. For a chemical change, we have to see a lot more. Hold it. There you go.
It's on the table.
Good. Perfect. Thank you. Now there's some clues for a chemical change. What's the clues for chemical change? Right? Release of energy. Form of heat. Right? Change in temperature. Formation of a precipitate. Change of color. It's going from white to black. And it looks really pretty. We stare deeply into the flames, you can see your future. The whole school shall burn. I mean, anyway. What I love about that, if you were watching the ash, you can see that the printing's still on there. Even after it's burned, the ink doesn't move. The ink has metals and other things in it that don't burn up. And so parts of it will actually still stay there from the ash. And you can still read parts of the thing. Even though it's turned gray, it's obviously a different substance. You got to let it heat out and fit a lot of the clues. And so that's my very brief demo between chemical and physical change. So let's see if we can't fill this in. Now I lost my pen. There it is. Now, one of the ones I'm sort of playing around with is that if we took that ash and we want to make it back into paper, how hard would that be? Really hard. It's difficult to reverse. But then, if you took the paper I just ate and you wanted to turn that back into paper, how hard would that be? Not as hard. It'd still be kind of hard, especially if you want to reconstitute it as the original stuff. All that ink's been chewed up. You'd have to get it all in the same spot. It would be quite difficult. But just to make it, you just have to like separate out the fibers from the poop, I presume, and then put it in water, reconstitute it, let it dry. You could probably make paper again. It's still there. It hasn't changed form too much. But this is a bit of a misnomer. There are some chemical reactions that are incredibly easy to reverse. We're going to do one later on when we do balancing, in which I ignite some balloons. But if you take water and you put it in a couple of electrodes, you can generate hydrogen and oxygen gas relatively easily. Some reactions go back and forth. All of these are just clues. They are not hard rules. They are not always true. Like most things that have clues, you just add them up and you say, how many of these do we have? The more that you have, the more likely it is that it's a chemical reaction. So someone mentioned a precipitate. What is a precipitate?
Like after the thing gets reacted, you get like a new substance from kind of leftover kind of thing.
But specifically, what kind of new substance is a precipitate? Like what is it? But what kind? You just said precipitate again, though. But what is it? Let's see if they have any of this solution. Okay. I've got some lead nitrate. You ever wondered their boomer grandparents are so weird? They know lead nitrate. Well, it's not lead nitrate. For years, we had leaded gasoline. Lead is a wonderful metal. You add it to gasoline, it actually smooths out, adds to the lubricant, and it has really slippery properties. It's perfect. It makes the whole car run better. It also gives off lead as exhaust, of course, and then the environment fills up with lead. It turns out that low levels of lead toxicity lead to an decrease in impulse control. It's correlated with higher crime rates. All sorts of bad effects happen society-wise when there's a lot of lead poisoning. One of the theories behind what killed the Romans. So we stopped putting lead in our gasoline, but we still have a whole generation of people that grew up. And as you get older and your body starts processing some of the older fats that were laid down when they were young, all that lead comes back out again. So we have two clear solutions. There's nothing in this, please. So what is a precipitate? Apparently not that. Did I say sodium chloride out loud? Because I'm supposed to grab sodium iodide. I grabbed the wrong chemical.
Yeah, get my class.
Try that again. Now, I grabbed the sodium chloride. It has a halogen. I was supposed to grab this one. It is also a clear liquid, and I forgot which one this was, so this might turn as soon as I put it in there. No, it's not perfect. So this is potassium iodide. Oh, that is a precipitate. We went to class. Yes. Go one. You can see it as I swirl this, it's got little solid bits on it. So precipitate is when you form a brand new solid that didn't exist before. This is, have you ever heard of lead paint? Yeah, very common to paint with lead paint in the olden times when your grandparents were young. If you, how many of you have seen Toy Story, the very first one? Oh, yeah. You know Sid's bedroom? If you look at the windowsill, he's got cracking paint on the side. It's cracked in a very rectangular fashion. That is classic lead paint cracking. Sid isn't mean or vicious or anything. He's suffering from extreme lead poisoning. All his behaviors are classic. It's not his fault. His family's poor. And it makes Toy Story that much sadder. Yeah. No, I just playing with toys. And well, it's kind of mean to his sister. Took her Barbies and ripped the heads off, and then like, yeah, it's true. Is lead paint cheaper? Lead paint, well, lead paint is cheaper because to get a brilliant yellow like this, you need a strong dye that's not going to fade. I mean, you want a good paint, you want a good paint. Lead as a chemical makes a very strong dye. It doesn't fade in sunlight because it's got a chunk of metal in there, gives it quite a robustness. So if you want a nice yellow, that paint's a nice cheap way to get a beautiful yellow. However, if you like ingest it, that's lead poisoning. That's not good for you. Canada, a number of years ago, I sent back, caused the company to recall a number of toys because the company that was manufacturing they were Big Bird, and which is yellow, and they're all painted with lead paint. And so they were actually, the company said they were intended for an adult market, but of course, it was in Costco. Parents saw, Ernie, Bird, Big Bird, and these little statues, so they got them to decorate their baby. Babies chew on toys. You can imagine you buy a nice crib, it's the 1950s. You paint a nice yellow canary on the side for a little baby crib. You give yellow trim, you're giving yellow trim with this. What do they tease on? The side of the crib. Lead poisoning came about quite commonly because of lead paint that we used to paint. Now lead paints are not allowed to be used for a whole host of areas. Because paint gets old, it flakes off, and then inevitably turns to dust. But once a nice bright yellow paint, so that is an example of a precipitate. A precipitate is a solid. So there was no solid there. They're both clear solutions. That's a clear sign that we've got a chemical reaction. Where did it go? Every time I sit down, I lose my thing. Oh, there it is. So if you get a new state formed, We get bubbles, we get precipitation, we get a color change. Now, some of you may be ESL and spell color without the U. Just a reminder, that's okay. If you're from the US and you're ESL, that's entirely fine. Do I have any Americans here to annoy? Oh, sadly not. Never mind. That will go nowhere. There's one. Question? Question?
No, I'm just telling him I used to spell it with the U, and then I thought people in Canada spell it without the U, so I started.
Oh, no. With you.
Oh, with you?
Yeah. Or a change in energy, and that's when we talk about temperature. Now, most of you have mentioned it getting warmer or heat being given off, but the opposite is also true. I have, it won't be today, but I do have a demo of a spontaneous reaction that gets cold. Most reactions that change in temperature require a change. So cooking pancakes is clearly a chemical reaction. They change in color. They're definitely different from the batter you started off with. And you have to add heat. That is the same as sucking in heat. So they had to have a change in their energy in order for that to occur. It's an endothermic reaction. I've listed a bunch of ones here. My favorite, of course, is burning. The flames cleanse all. The school has burnt down once and Whittle House twice. And one of the ones I like to mention specifically as a reaction is cellular respiration. From grade 11 or grade 10 biology, what's cellular respiration? Yeah, what do they react with? No, oxygen and, yeah, what was the oxygen reaction?
Oh, I think
It's in your blood.
Yeah.
It's CO2 plus H2O plus ATP if you're in like biology 11, or plus energy if you're in biology 10. What is it that your whole body burns for energy? Did you say tofu? Yeah, but what is the chemical that has to get to your cells in order for it to burn energy? Sorry? Carb, yeah, it is a carb. But which carb? It's a very specific carb. You measure this if you're diabetic, if you know any people or glucose. It's close. It's a sugar. And those other sugars are broken down and shoved into the same system or remade into glucose. It is your whole body runs on glucose, sugar. And if, for example, you are starving and you need to digest some protein for energy, you actually turn it into sugar in a way, and throw away the useless nitrogen, and you throw it into the same system. You can actually starve to death eating protein because of this. There's something called rabbit starvation, in which if this has occurred, if say you're up north, you get snowed in, and there's like, winter hares running around, little white rabbits that you hunt to get you through when you're snowed in. Because your body has to process the protein to turn it into something like glucose in order for you to burn it, the protein itself, it can't do that. It needs a little bit of fat, and rabbits are so lean, they don't have enough fat for your body to do that properly. So you actually can starve to death while eating rabbit. So if you are ever in that situation, make sure to crack open its head and eat the brain too, because that's about the only source of fat that's in there. You're welcome. for that image. Yeah,
How big would your rabbit's brain be? Like,
yeah, it's not going to be a tiny thing. Yeah. I would highly recommend you cook it in whatever fashion you find boiling will work. Yeah, but you know, a little pan fry with some salt and pepper might be good as well. Yeah, put a little, get a nice little crust on it. Yeah. This process, to just highlight how important this process is, this is the entire reason that you have lungs moving around your body. Your brain doesn't work unless you get the glucose every single minute. It requires oxygen and glucose. And if that drops, you get brain damage. Your circulatory system is constantly bringing glucose and oxygen to your body. You have entire organ systems dedicated to just regulating this process. Because you're constantly producing CO2, your body is constantly becoming more acidic, which means you need your kidneys to keep that in check. If you've ever heard of diets that are called like alkaline diets or acidic diets, you can ignore all of those. That's what your kidneys do. They do it really well. You don't need a special diet to be able to. If you did, you would die every time you ate a lemon because the acidity would kill you. All your organ systems, I actually can't really think of one that isn't dependent on this, and this is all just going on in your mitochondria. Even the reason you exist, the reverse of this is cellular respiration. But what is the reverse of this? The foundation, pretty much for all, well, I can't define it because then I will be giving it away. Well, I would say all plant life depends on this for food. Photosynthesis. It's important enough that we used to think that no life could exist on this planet that didn't rely on photosynthesis. Even carnivores eat herbivores that eat plants. It's only now that we've found a few volcanic vents that actually create things without photosynthesis, but they're very rare.
It's going back to the pancakes.
Yeah.
So if, like, say we're going from like the separate ingredients to then the batter, would that be
What would your guess be? Yeah, because it was like the water before you, or milk before you added it was wet. Now the whole thing's wet, but it's still the individual components. But batter to pancake, it's chemical. You've added energy, it's changed color. Colors that weren't there in the original one have appeared. So you've actually, and that process by which things go brown is called the Maillard reaction. And it produces very complex proteins and carbohydrates from that reaction, that browning process. Really important for flavor. A lot of them can't be predicted, and it produces a huge variety of flavor compounds. So that's why in a lot of cooking, you want to brown it, and then you pour a bit of water or wine or something in, you get that brown stuff off the bottom of your plant because that's what's actually tasting good. Okay, how to write an equation. I'm assuming this part is completely review, but I want to make sure we do it. Hold it, did I do everything on this page? I am missing reaction, chemical change, clues. I am missing an entire page. I am sorry, you just had to add this somewhere. You're missing that page, I'm presuming? You don't have this? It disappears from mine too. It should have this here. I'm sorry, it doesn't. Just add this to the bottom of the first page or in the back or a corner somewhere. I just wanted to, since we defined physical change, chemical change, I want to define chemical change. Since we define chemical change, I want to define physical change. Physical change is usually defined in opposition. So you have no new substances. No bonds broken. No bonds reformed. Tearing something, dissolving it, breaking it down by physically pounding it into a powder, it's still the same substance. Powdered sugar is still sugar. You can, however, get new things that fit, so a change of state. So over here we said, oh look, did I move this whole thing? Oh, there we go. I said a new state form, you get a bubbles, precipitate. A precipitate is a solid. But over here, a change of state, if freezing or boiling, you get a gas being formed, or you get a new solid being formed. So you do have to distinguish, are we getting a brand new solid, or did it just freeze? Because frozen water is still water. But that lead iodide I made didn't freeze. That is a brand new substance with new properties, new colors. So they can often look similar. That last one there is to provide your own example. Give me an example of a physical change. Yeah? Yeah. But first you have to give me an example of a physical change. Just changing, just heating it up? Sure, that'd work. In fact, that gives me an opportunity. If you heat water 50 degrees, 50%. 50 degree. Hold it. What's room temperature? 20 degrees. 20 degrees Celsius to 80 degrees Celsius. Ooh, yeah. Physical change. But if you heat pancakes, if you're heating pancakes, some of that heat didn't go into changing the temperature. Some of that heat went to breaking and reforming bonds, and you made a pancake. And some of that heat was absorbed. And that would be really difficult to tell apart if you just went down temperature. We're also going by the pancake change. It went from liquid to a solid. It changed in color. It changed in flavor. There's a lot of things that changed about the pancake that didn't change in the water. All the water did, all of the heat that went into the water changed its temperature. But some of the heat that went into pancakes actually chemically changed it. It absorbed the heat. So cooking is a chemical change, but just boiling water is a physical change. State symbols, when you're writing an equation, you put state symbols down the bottom. What does S stand for? Solid. L, liquid. G, gas. And the piece de resistance, AQ, aqueous. Did you say acid? It's not an acid indicator. That would be indicated in a different way in an equation. So AQ stands for aqueous, which specifically means that we dissolved it in water. We dissolve things in water so much. I just showed you a reaction where I had two things dissolved in water. The water is just there to carry the chemicals around. And we do that so often, we have a specific state symbol for it to say that it's dissolved. It's AQ, and it stands for aqueous. It just means it's dissolved. It's not melted, it's dissolved. When you put a number down below here, what's that called on like a typewriter? Like down below, what is that called? It's a subscript. Gives you the number of that element. We've already done this because we had to do nomenclature, but just to go over as a full reaction. What's the number in front called? Coefficient. Just like the number in front of brackets in mathematical equation. The things on this side are known as reactants. The things on this side are known as products. If any here in Bio 11 AP? Have you done enzymes in equations?
In equations.
Yeah, like reactions, not quite yet. They use a different term for it. Instead of reactants, they'll use substrates. You talked about substrates. So yeah, the same term. Oh, yeah. Biochemists want to feel special, so they came up with their own name. And it does indicate to who you're talking to, it's not just a reactant, it's a reactant that fits in an enzyme. And so that gives them a little extra to play around with. So then a reminder, the things that are present at the beginning of a reaction is called what in A? Slates. And the chemicals at the end, Logan? This product. What I'm looking for. Reactants become products. That looks good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Jada, was there someone beside you or something? 12, 13, 14, 15. That means we don't have quit. That means I can't just say go in pairs. No, that means I'm just going to assign it. Yeah. We'll see who the lucky person is. Chemistry 11. Toolkit. Group maker. 2. Nice. Luke, you can join whoever you want. Everybody else, get in pairs and write that equation on the board. Dylan, how did you? I think Taylor went to the bathroom. Taylor? Yeah. They will be back in a moment. Find a spot on the board. I will point them in your direction. Grab a pen, write the equation on the board. Can you write you draw lines? Which you can use the other half of there. There's lots of room on that side. You'll be happy to know I finally finished that piece of paper. That piece of the periodic table is now inside of me. You're with us. Okay. Excellent. All state symbols, they will open reactions to the box, and you should have no charges on it. But you're very close, yeah, you got the important. Hold it. Yeah, you're fixing that as well, so, there you go. Oh, yeah. We just call them. All state symbols. All state symbols. It formed the same with the blood nitrogen. That's a really good one. I never thought that someone would interpret that. Oh, yeah. But at the end, you should remove all your positive. There you go. By the language. So there's sodium chloride. It formed a cloud of silver, chloride. So that's like exactly like the lead nitrate. You see a cloud forming in the liquid, just like the yellow stuff. So what does that mean? Oh, so that means something. What you have there. Drop into a solution of silver nitrate.
That's an aqueous compound.
So it's not a solution.
Along with another aqueous compound.
So exactly like I know the cloud of yellow crystal form. So a cloud is actually the cloudiness of it. There will always be an energy change. You don't always have to put in some energy. No, you can salt in water. Like you take salt, you put it in water, you mix it, you know, salt water. That's aqueous. So if you had a crystal of sodium chloride, solid, but then you had a solution of silver nitrate. If it's solution, then it has like a polarity. That means it's dissolved, so it's actually aqueous. Yeah, that's what a solution means. It's dissolved in water. Yeah, that's what a solution means. You put water. So, like, if I have a silver nitrate solution, I have like a 0.1 molar solution of silver nitrate, which means it's water. Yeah. If it was ever not water, we would have to specify because all of chemistry runs this. You'd have to specify what liquid, because you solve it in ammonia. Solid, aqueous, solid, aqueous. You're telling me on your formulas, because it's capitalized. No, it's not capitalized. Now it makes. Because it goes from silver chloride to silver carbon weird lithium. Oh, is one of those capital and lowercase? No, capital is this. Oh, capital? So the problem is that your lowercase looks a lot like my capitals. Oh, yeah. A single line. Okay. Please check and correct your own. They should all go. It's a crystal of sodium chloride, so solid, and then a solution of silver nitrate, aqueous, and a lot of people put liquid. A solution is dissolved in water, so that's actually here. And then it makes silver chloride a cloud, and a lot of people start putting gas. That is a solid, it's a cloud forming in solution, that's precipitate. And another aqueous compound, which most of you got NaNO3, which is also aqueous, so that was good. So fix it, and then I'm going to give you another one. A cloud is solid. Because it refers to this is a cloudy solution. Right? It refers to what it looks like, not the state of the substance. Yes. So solutions are things that have molarity. They're always Yep. Let me give you another one. Up the complexity side. Yes, if then or a solution or this molarity, then it's aqueous. Yep.
And then for determining molecular compounds, does that say specifically it could be a liquid or a gas?
It could be a solid, liquid, or gas. Yeah. It would have to say outright. Okay, new partners and a new thing. So there's your new partners. Milan, you can go with anybody, so you get to pick your group. Find your new partners and find a spot on the board. Ha. I split up Dylan and Jillian. Oh, I'm gonna show you. Has everybody got their partner? There's your one, and I put another one below it. Do the first one first. Second one, if you finish that one, call me over to check. Consult with each other as well. Groups consult with other groups. What do you know about this? Your NO in your first NaNO drink, that O is really small. That looks like Philadelphia. Yes. And then you can assume that that's a salt. Plus, I'm guessing you got the industry index. And so you box up, and then you get this thing. Start the second one. Yeah. We have 3 solids. What's the charge of two? Yeah, 2 and 3. Nice. Yeah. A reaction with carbon dioxide gas. I need a plus sign between that and the last one. The only thing I'm missing. Are you? And aqueous sodium bromide and and water. There you go. Yeah, it's a lowercase L, just be pedantic, but good. Nicely done. How about the groups? Yeah. Yeah. Probably so. Yeah. I'm asking. You don't get oh, but this breaks apart, so it's yeah. And it's a sodium with a sodium. You don't have to balance them, by the way. If you're going crazy trying to balance the first one isn't difficult to balance that problem. And your NaCO3, and your liquid should be a lowercase out of that. So we can get the NaCO. What's the charge?
I just made that. You know what?
You don't have to balance, but you're so. Thumbs up. The HBR strong. No, it's not. It's too long.
Let's see.
Almost 200. Must be not that one. Yes. All the water. It has a liberty. It is. Oh, and you immediately, I was just about to say, everyone who is not quite done, go look at that hairs. But no, you keep that knowledge to yourself. Don't share that. You don't share it at all. It's okay. Hey, this is solid, aqueous, gas, aqueous, and liquid. The L should be lowercase for the liquid. No, it's right. Yes.
Okay, I'll show you. Look, now, this is uppercase, right? That's lowercase.
Yep, but that last one, that's just a messy capital.
No,
Capital. Is that lowercase L actually an uppercase L? If I wrote that on the board, would that be my messy writing?
Which one of the three is uppercase?
Thank you, Tim. Okay, it looks like everybody has gotten it. We got a nice gas, aqueous, so perfect. Thank you. Oh, what time? 11:45. We still got some time. Okay. We are not doing this demo today. We will do it on a day that the lab is not being used by other people. And I will preface this by saying that I've set off the fire alarm twice doing this lab. And both times completely abandoned my class. They were just wandering around in the lab, wondering what to do. My spawn actually said we should go outside and directed them up to the houses because that was a grade 10 class. If the fire alarm goes off, I run to reception to tell them it's just me. And then they have to tell all the other teachers, then we have to turn the alarm off. So if I go away, then you have to walk up to the field and line up. I may run back very quickly, so just hang on like 30 seconds, because last time I got permission from Mr. Sullivan to tell everybody not to go outside, because it's just Mr. Neufeld doing the demo again. So that demo is coming up. Hopefully we don't set off the fire alarm, or hopefully we do.
Yeah.
I don't like setting off the fire alarm. When I set off the fire alarm, Ms. Hedquist has to leave her class. And then she gets angry at me. And I am afraid of Mrs. Hedquist. How many of you are afraid of Mrs. Hedquist? Yeah, okay, yeah. Yes.
Is it possible for us to do hydrogen balloon explosion in the lab?
That's what we'll be doing. Yeah. Okay. Law of conservation of mass. Again, this is something you would have learned last year. This is just telling us that the number of atoms on each side of the equation. Why am I doing that in green? It's the same as everything else. There we go. Atoms. Whatever you start with, you have to end up with. Nothing can just disappear. And you can't just mysteriously add chemicals. So in these reactions, for example, I think, let's see if I can pick one that's here. I'll use this one as an example. If you're looking at a reaction and somebody missed, they didn't put the plus H2O because they didn't see that it said add water. That's fine. However, if you're looking at this, you would immediately know something was wrong because we have CO2 and we have NABR. But if I do this, what chemical is missing? Hydrogen. That hydrogen has to go somewhere. Law of conservation of mass means that atoms don't get created or destroyed. And they have to all come up. Balancing is just the process of making sure that the numbers are correct. So the same number of hydrogens you started off with are that you end up with. And it's our artificial method of trying to predict what actually happens. When we balance, we're making a guess. It's often not that. Usually what we take as, oh, it just does this. No, actually it does it in 5 different steps. And there's actually 5 mini reactions where it really occurs. But overall, it has to be. It's just a law of chemistry. You can't make matter disappear. Now, I'm obviously lying because we do that all the time. It's called nuclear reaction. But we're not going to exclude nuclear reactions because we're just going to focus on non-nuclear reactions. So this is absolutely true. If we talk about nuclear reactions, the law of conservation just differs. We just say it's the law of conservation of mass and energy. Did you say how? What was your question? Nope. Does anybody know the famous equation that relates mass and energy? The most famous equation in the entire world. Equals mc squared. What Einstein discovered. If you take a certain amount of mass and you make it disappear, you get that amount of energy. And so a nuclear reaction, some mass does disappear. And that's why it turns out c just is a constant, stands for the speed of light, and it's a really large number. And then you square that, and you make a really, really large number. And then you multiply it by the amount of mass that disappeared. That tells you how much energy it comes out. So a very tiny number multiplied by a gigantic number squared still gives you a very large number. And so if we were breaking this, we end up dealing with huge amounts of energy. That is what powers our sun. We're not going to get to that level. Very exciting news. They just did a successful experiment on nuclear fusion the other day, in which they managed to produce more energy than they put into the reaction. It took them more energy to create the things that then put in the energy. So it's still not a successful nuclear fusion reactor, but they say it's about 50 years away from working. Just so that you're aware, they've been saying it's 50 years away for 50 years. But once we do accomplish that, we have a very clean source of energy that doesn't produce radiation that we can then use, which would be great for our whole greenhouse gas problem. Currently, just to give the weigh scales, if you are burning coal for energy, you produce more radioactive waste than a nuclear power plant. Because there is radioactive waste in coal, and you burn it, and it spreads out all over the place. We would like to have none, and that's what we're hoping nuclear fusion will do. Okay, matter can neither be created nor destroyed, which I then hinted down here, except in nuclear reactions, which never happened. It's only the most common reaction in our solar system. And then I use this reaction to graphically, what was that? Sorry, I just looked to see if someone was genuinely injured. Nobody's running from the Iowa station. They're great ants. Okay. Oh, is it meta? No. Really? Oh, okay. They look shorter for a moment, but then again, I'm tall. Everybody looks short. Okay. For every single reaction that you do, when you're balancing, you take a look and you go, oh, I have one carbon here. I have one carbon there. It balances. I've got 4 hydrogens there. I've got 2 hydrogens there. It doesn't balance. What do? Do we just add 2, like 4? No, stop that. What do? No, I don't want the answer. I want the process. Balance. Well, how do we balance? Yeah.
So I took a look at the H's in the first CH4.
Yeah.
And then I did 1 CH4 and then I did 2 H2Os.
Right. Because you need double those amount of H's. So you only put numbers in front. Because we can't change the nature of what's there. It's always going to be water. It's always going to be H2O. Then what did you do?
So now we got, I did 1 CO2 because we got 2 O's on that side.
Mm-hmm.
And then now we've got 6 O's on that side, on the right side. And then we got to add 3 O's on the left side.
Well, we have, you said 6 O's. How many O's do we have on this side? 4.
Oh my God.
You just made it harder. Yeah. But if there are 4, what number needs to be on the front here? 2. Now, this process is very artificial. We as humans are doing this to understand what's actually going on. We can represent it below graphically, and this is more of what actually happens. This methane particle gets all of its hydrogens ripped off. So an oxygen will take off 2 hydrogens, and when it does that, it'll let go. And so it becomes a single oxygen with 2 hydrogens. That oxygen will take 2 more. A naked carbon is very reactive. And if there's oxygen around, it's going to bump into it and also rip its electrons apart. And so it gets sandwiched in between into carbon dioxide. Every single element has to be accounted for. So we can see here physically, there's 1 carbon on both sides because that carbon had to go somewhere. If it had 4 hydrogens that react, we needed 2 oxygens to fully react them all in. So of course we get 2 H2Os. If we were doing it and seeing the atoms move, we're getting closer to the true explanation of what's happening. Balancing allows us to predict that, and it's the reason we do it. It also allows us to predict things. If I say if this is 1, 2, 2, 1, I can now do things like say, but I have 3 moles of CH4. How many moles of oxygen will I need? Pardon? 6. Because for every 1 of these, we need 2 of those. For every 3 of those, we need 6 of those. And now we can find how much water will I make? 6 moles. And how much CO2 will come off? 3 moles. And now I can say, oh, wait, I measure oxygen in liters of gas. 6 moles times 22.4 liters per mole. I can now calculate the number of liters that I'm going to need to do this reaction. And so now our moles are going to come in here. This area where we start putting numbers into it is known as stoichiometry. And it's where we get to do these reactions with all of these numbers and moles. Now, we're not doing that yet. We're going to do balancing first, give you a little reminder on that, give you some practice, but that's going to be coming. We only have 5 minutes left. I'm going to stop it there so we can pull out the spreadsheet and see what our homework is. Reactions and balancing. Okay. Ignoring this section and that, spend the last 5 minutes just trying to balance those 5 equations. Yeah. I've just added them in. Yeah.